at 2, right? Then what I would do is take that formula again, replace the a with 2, 2 to the 4th. So we get negative 3 over 2 to the 4th is 16. So we get negative 3/16, right? And so on and so forth. Look at that formula for a second. Can anybody tell me something kind of interesting about every slope of every tangent line, no matter what point I'm ever at? What's that? Positive. Not positive, close. The bottom's always positive, right? A to the 4th power is positive. But then you have on top negative 3. So negative divided by positive should be negative. So all of our slopes will always be negative, right? No matter where you are on this graph, the slope of the tangent line will always be, looking at it this way, will always be negative, right? With one exception. There's one place that this is not defined. What's the one value of a that I cannot plug in here? 0. But remember the original function was what? What was the original function? 1 over x cubed. Well, can you even plug 0 into that? No, you can't plug 0 into that. So don't worry about the fact that that slope of the tangent line doesn't exist at 0 because the original function isn't even defined at 0. I want to look at the graph of that. And I'm going to try, by graphing this, I'm going to try and make a connection to something that we're going to be talking about later. But there's no reason we can't discuss it now. So, does anybody have a question as to why this is always negative? Everyone understand why that's negative?
Is it just for this one that will?
For this particular problem, right? For this particular problem always, sorry. For this particular problem only, the slope of the tangent line is always a negative number, right? Look at the graph. There's the graph of 1 over x cubed. Do y'all see that if you go anywhere on this graph, your slope of your tangent line is negative no matter where you are? Like, I think it's obvious right here. Like, if I go to that point, right, the slope of tangent line is negative. What about this point? Negative slope, right? How about way over here? It's hard to see it, but that's negative. Let me do a standard zoom on that. That's the standard zoom. See, this is coming up asymptotically approaching the y-axis. So if I go over here, I'm going to have, it's not quite flat. It's going to have just a little, tiny little slope to it, right? But it'll be negative. It won't be like this. It'll be down a little bit. Same with over here. If I come over here, negative, 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 right? Always a negative slope.
So if we get something like this on the exam, we just have to find the slope. We don't have to use those points, those x's up there.
If we get something like this.
Because we have find it with
Like if we have to do all the
I gave you all 10. So no, what I will ask you on the test is, here's the function, find the slope of the tangent line at A. That's what I'll ask you. And then you will just find, and then your answer would be the negative 3 over a to the 4th power. Box it up, that's your answer. I want to do one more before we move into the next idea. It's not really a different idea, but let's do one more example. How about f of x equals, let's go with 3x to the 3rd minus 4x squared plus 1. I want to find the slope of the tangent line at x equals a. So this is the way it would appear on the test, something like this. That's not a quadratic function, right? It's cubic, right? So, all right. Well, I'm going to just grind out the definition of the, we know what the definition of the slope of the tangent line is, so let's just grind that out. Slope of the tangent line, right, is equal to the limit as x approaches a of f of x minus f of a all over x minus a. If you look back in your notes from today, this is the first example of a function I've given you that has more than one term in it. Everything else I've given to you has only had a single term. Now we actually have 3 terms, right? So we have to just be careful when we're plugging things in here. Let's see where we are on our list here. We are at Enrique. Where's Enrique? How's it going, Enrique? Good? Do you have any questions before I ask you? You're good? Okay. So this is limit x approaches a. Enrique, what is this? That thing, right? Okay, so I'm going to put 3x cubed minus 4x squared, right, plus 1, right? And then, Enrique, I'm going to go minus, and now what's f of a? Yeah, same exact thing that we see up there, but replace all the x's with a's. So if I do 3a cubed minus 4a squared plus 1, Enrique, is that correct if I write it like that? Exactly. I have to have parentheses around this. Why? Well, because I'm subtracting everything here, right? Whatever the function is at a, that's the function at a. I'm subtracting the whole thing. So you have to have parentheses. And then all of this is over x minus a. Right? Good. Distribute the negative through. Yeah, I think something does cancel there. Let's see what happens. Let's go. Limit x approaches a. We're going to have 3x cubed minus 4x squared plus 1. Now distribute the negative. Negative 3a cubed plus 4a squared, and then minus 1. That's just me passing this negative through the parentheses here. What happens if you forget the parentheses? Yeah, it's over. At that point, it's over. All right, your algebra is never gonna, nothing's ever gonna cancel. All right. All right, but we do get the ones to go away. Right, that's better than nothing. Right, the ones do go away here. And so I have limit x approaches a 3x cubed minus 4x squared plus 4a squared. Shit, I'm missing something. Hold on. Minus 3a squared. I'm sorry, 3a cubed plus 4a squared. All right, I think I got that all. All over x minus a. I'll take a volunteer. We have to try and factor this. Our ultimate goal is to get an x minus a to go away, right? We've got to try and factor that. Any ideas? What? Try grouping. Why are you thinking grouping?
Because we want the x. Because we want to get x and a.
But why grouping? I agree. We want the x minus a to go away, but why grouping? So, okay.
I have 4 terms.
4 terms.
2 of them match each.
Yeah, so normally when you see 4 terms, you think grouping. Was there a suggestion, sir? No. Were you thinking grouping as well?
But there's the variables aren't the same.
The variables aren't the same, so this may not work, okay? But we try grouping, right? Yes?
This is what, I don't remember exactly this one. You take the x out of the first 2 terms.
So we could try and pull x squared out of these 2. We could try that, and then you could pull what? Okay, so let's hit the pause button for a second, okay? Because we got to do some algebra here. And there's different ways we can go down, different roads we can go down. So I'm going to take you down the wrong road first, all right? So let's see why this isn't going to work. If I take, this is scratch work over here, okay? If I take 3x cubed minus 4x squared minus 3a cubed plus 4a squared, like that. If I try to do grouping like this, where I look, this is the way I teach to do grouping you. Right after the second term, you put a little slash there. And then on the first 2, you pull out a GCF, if you can. So can we pull out a greatest common factor? X squared. What are we left with in there? 3x minus 4, right? That's what would happen if we pull out an x squared from the first 2. And then in grouping, you have to do the same thing over here. You try and pull a GCF. Can we pull a GCF out of this? You can pull a squared. And because I'm pulling positive a squared, I put plus a squared. And then what's left in here? Negative 3a plus 4, right? And we have multiple problems, issues why this is not going to work. For grouping to work, this has to match this, right? They have to be exactly the same. Now, you could pull a negative out, couldn't you? And that would make that positive and minus, which would match here. But see, this is x and that's a. They have to be exactly the same. So grouping fails if I do it this way. Y'all see that? Okay. Nope. All right. So that's not working. The frown is optional.
Would you put the highest exponents? Would you combine?
Yeah, so maybe we can rearrange and try something else, all right? Maybe. So I'm going to rearrange. Can I erase? I want to keep that on the board. Can I erase this? All right. So now what I'm going to do is rearrange this. I'm going to write it as 3x cubed. Then I'm going to bring the minus 3a cubed. And then I'm going to put the minus 4x squared and then the plus 4a squared. Right? I'm just going to see, maybe rearranging it will help. If we try the grouping again, let's just try the grouping. Is this going to work? Pull a 3. Right? You can pull a 3 out of these. 3, what's left inside? X cubed minus a cubed, right? Now over here, can we pull anything out? You can pull a 4 or negative 4, your choice. I'm going to do negative 4. What's left in here? X squared minus a squared. Shit, that didn't work either, right? Because these have to match exactly, don't they? However, this is a difference of cubes, and this is a difference of squares. So there's still more factoring I can do here, right? So I'm going to continue. Even though these don't match, watch. This is 3, and now everything in red here, I'm going to go to my formula sheet, and that becomes x minus a times x squared plus xa plus a squared. That's what that difference of cubes turns into. Then I still have minus 4. And then everything here, oh, geez, doesn't want to. Everything there, that's a difference of squares, right? That turns into x plus a, x minus a, right? I realize this is not pretty, but this is why I gave you the example. This is the last example before we move on. So just showing you how the algebra can be messy. Y'all all right with this? I mean, not all right, but do you see what I'm doing? All right, looking at this and this, do you all see something in common in both of those? X minus, wait, what was it? X minus a. And if I pull that out, it's going to cancel with this x minus a, isn't it? Which is what I want, right? So at this point, I'm going to pull out an x minus a. Now, I'm going to use a bracket, even though brackets and parentheses are identical. This is just to really stress to you that out of these two, I'm pulling out this guy and this guy, right? So when I pull x minus a out of here, I'm left with the 3, and I'm still left with that, right? So I put 3, x squared plus xa plus a squared. And then I still have over here minus, and then I pulled this out, so I'm still left with the 4 and the x plus a. Close my bracket. Hopefully you see that if I distribute this to here, I get that. And if I go here to here, I get this. You'll see that algebra? Any questions? Well, now, remember, this is just scratch work, right? So now I'm ready to come back over here now, okay? And yes, I will cancel now. But I'm going to come back now. All right, so here's where I was. I was at the limit. X was approaching a. This entire numerator, right? This entire numerator is this. So it's x minus a, bracket, Then I had 3 parenthesis x squared plus ax plus a squared. And then I still had minus 4, and then I had x plus a, and then close the bracket. All of that over the x minus a. We're very close, because now we get the factors to cancel. You didn't realize how fun this was going to be, did you? That's the whole point, is to get the x minus a to go away. We want that thing to go, because now we should no longer have division by 0. We should have something meaningful when we let the x go to a. So limit x approaches a. All right. Well, yeah. You know what? Can I just do it? Can I do the limit now? Can we just imagine these are gone, 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 and now let x go to a? So I will have 3 parenthesis, x is going to become a. So a squared plus a times x, a times a plus a squared. All of that. Then minus, then over here 4, and this is going to be a plus a. Do what's in parentheses first. That's a squared plus a squared plus a squared. How many a squareds? 3, and you're hitting it with a 3 on the outside. So 3 times 3? 9. You get 9a squared. Not plus, minus. Minus 4. And then what's a plus a? 2a. I guess I could have done what? This is 2a, right? 4 times 2a? 8a. Done. Now I realize some of you in here have seen calculus before and are very aware of the shortcut that you can do to get the same answer. Right? There is a shortcut for those of you who've seen calculus. I know. A lot of your classmates haven't seen it, so everyone's going to get the shortcuts at some point. We're not ready for it. You have to suffer through the limit first. There's our answer, our generic answer. Now you can give me any value of x equals 2, x equals 5, and I can just push it into that formula and that'll spit out slopes of tangent lines. Yes?
If we know the shortcut, are we allowed to use it?
You can check your answer. So on the test, well, on the first test, we haven't talked about shortcuts, so if I ask you for something like this, you have to grind it out. All right. So we're not done with this section. I just want to tell you right now in the homework kind of what you can do. The problems that are really important in this section are I'll put it on the side right here. This is from 2.1. 21, 23, 25 through 30. So 21 and 23 is like the first problems I gave you, where you actually are finding the slope of the tangent line at some specific point. And then 25 through 30 is where you're trying to find the slope of the tangent line just in general, generic, all right? All right, we still have a long way to go here. You all right? We go till what, 5:15? What time do we get out? What, 4:30? All right, make sure you stop me. (21, 23, 25 through 30). All right, so what I'm about to do now, you're probably not going to like, all right? Because we've just become comfortable with this idea, right? This idea of you have this point A, this point, X, and then you drag that point over. I'm going to go through that entire idea again, but using different values. Yes?
Is this 2.2?
Still 2.1.
Okay.
Still 2.1. So I'm going to go back to my notes. All right, and what I'd like for us to do is look at 2.1.16. We are going to do a second approach to everything we just did, another way of looking at it, all right? So remember in the beginning, I chose this point A, right? And then that second point I picked was, I called it X, right? I'm going to do something different than that. What I'm going to do is I'm going to pick this point A, and then whatever that point A is, I'm going to pick another point over here, but I'm not going to call it X. I'm going to call it A plus some amount. So do you all agree that if this is A, and then I add some H to it, I'll be over here? Yeah? So if that's A plus H. Think about it this way. If that's 3, what happens if I add 1? 3 plus 1 would be 4. It would be over here, right? So this is A. This point here is A plus some amount. So the distance from here to here is H. So where I used to say, call this X, right? This used to be X, no more, right? I'm calling it A plus H. And then we're going to draw the whole picture again and come up with a new formula, a second version of everything we just did. Right? So here's our first point. A, f of A. Nothing has changed. The second point, however, is the x coordinate we said was A plus H. Right? That's the x coordinate. And then the y coordinate is what you get when you plug A plus H into the function. You'll see how that's different than before? I mean, in the previous version, this was x and this was f of x. Now this is A plus H and f of A plus H. And I know you might be asking, why are we doing this a second way? Like, we have a way that works, right? Like, why don't we just stick with that? Well, it comes down to the fact that these two definitions, sometimes it's better to use the first version and sometimes it's better to use the second. Your algebra changes depending on which formula you use. So sometimes we want this one because the algebra is better. Sometimes we want the other one because the algebra is better. You'll have to see when we work through some examples, all right? So we've got this second point, and then we do the same thing. We draw a line, and let's write down on the side here, what would the slope of the tangent line be? What would the slope of the tangent line be? Still y2 minus y1 over x2 minus x1, right? So for us, what's y2? Yep, this is y2. And we're going to subtract from that f of a, right? So y2 minus y1 would be f of a plus h minus f of a, then all divided by x2 minus x1. What's x2? A plus h. What's x1? A, right? And the a's cancel, and you get this formula right here. The slope of the tangent line, I'm sorry, I messed up. Sorry, this is secant line. We haven't moved it yet. My mistake. Slope of the secant line would be f of a plus h minus f of a all over h. I'm wondering if any of you all recognize that from college algebra. Yes? Do you remember what it's called? No? The difference quotient? Do you remember that from college algebra? That is called the difference quotient. And in college algebra, your professor's supposed to drill that thing into you, like he's supposed to beat you over the head with that and make you practice doing it over and over and over, because when you get to calculus, you need to be able to compute that. But that's okay. If you haven't, don't worry about it. All right, so that's the slope of the secant line. Do y'all see how it's the same construction as before, but just different, one thing has changed. This is not x and f of x. This is a plus h and f of a plus h. Otherwise, everything else is the same. Now, if I move, right, let's move it. If I take that second point and I move it over like this, right, and try and drop it on top there, right, we have a problem again, just like we did before, But what I want you to think about is how would you move if this is A and this is A plus H, how would you move this way? Previously, it was just say, hey, let X go to A, right? Because this was X, that was A. We said, hey, let X go to A. What would I do here to make this go to this? Subtract H. How about making H smaller? What would happen if I made H smaller? What would happen? It would start sliding over here, right? Smaller H, smaller H, smaller H. In fact, I'd like H to go to what? A plus H needs to go to A, but we need the value of H, which is the distance from here to here. We need that value of H to shrink down to nothing. So instead of our limit, remember our limit before we said limit X was going to A? We don't want that limit anymore. What we want is a limit where we just let that H shrink to nothing. If the H goes to nothing, then this point moves over to this point. Do you all follow that? Okay, so you kind of have to look at the old picture. The old picture, this was A, right? And this point right here was X. And so to move this point over here, all I had to do is set up a limit and let X go to A. And I think, at least nobody complained, that idea just slides this X over towards this A, right? Yes? Here, if I'm calling this A and this A plus H, the only way to make this A plus H slide that way is to make this number get smaller. Imagine that this number is, let's say it's 1, right? If this is A plus 1. That would be one unit away, wouldn't it? But if I said this is 1/2, now you're going to move even closer. And if I say that's 1/10, now you're real close, right? If I say that's 1/100th, you're even closer. Ultimately, I'd like that H to go to 0. So it actually moves that right on top of the other one. That make more sense? Okay. So to get the to get the slope of the tangent line, right? This is the slope of the secant line. To get the slope of the tangent line, all we're going to do is set up a new limit. H is going to go to 0 instead, and we're going to use that formula instead of the one we had before. And I have this in the notes. I just put it up there so that I could talk through it. So let me bring it up in the notes. Here it is. Here's the definition of the slope of the tangent line if we're using this new construction of A and A plus H. Slope tangent line is that limit right there. Okay? And then the equation of the tangent line, right, that's just the slope. The equation of the tangent line will be exactly the same as the equation before, right? We had y minus f of a. Over here we had x minus a. The only thing that's changed is this. Instead of going x to a, f of x minus f of a over x minus a, it's now limit h goes to 0, and then this new ratio. So I want to show you these two side by side. This is like the big note, I guess the big note for today, for 2.1. If you've got some curve, right, and you're trying to find the slope of the tangent line at some point a, f of a, then you have two options on how to find that slope. You can use that formula, or you can use that formula. You get to choose. Not many times in math that you have choice, but this is one of them. You get to choose which formula you want. Similarly, or not similarly, I should say, and if we extend on that, now if we talk about the equation of the tangent line, right, the equation of the tangent line at that point, then again, you have two different formulas you can use. The only difference between the two is the limit that you use. All right? So what do you think I'm going to do now? I'm going to give you some examples, right? And what examples do you think I'm going to give you? How about we do the same examples we've already done? At least some of them, right? Let's do some of the problems we've already done today using the second version of this and see if the algebra is better or worse. How about that? That sound fair? And we'll, maybe in working some examples, we'll make some determinations about which one was better, right? Like say, oh, yeah, I really like that one. Now, as a little bit of a, what do they call it, spoiler, the second definition is the one that we use almost exclusively as we move forward. The second one, the one I'm about to show you. But I will say, do not marry one of them. All right, marry as in like don't commit yourself to one. Always be open to using both. All right. All right. So what was the first one we did? It was x squared, right? So let's do f of x is x squared. And let's find, is it all right if we just do the slopes and not do the equations? Because once we get the slope, the equation we can just plug in, right?
It was x cubed.
First one we did, very first one today. It was x squared, and then it was find the slope of the tangent line at x was 2, right? Slope of tangent line x is 2 was the first one we did. Yeah. All right, so definition, the slope of the tangent line using the second definition is the limit as this time h goes to 0, f of a plus h minus f of a, all of this over h. That is the definition that I've just established. What's a? 2, right? 2. So I'm going to plug 2 in now for a. Limit h approaches 0. F of 2 plus h minus f of 2 all over h. That's just me replacing a's with 2's. And I'm going to try and get through everyone today. Let's see here. Who am I missing? Jenna? Have I called Jenna? Jenna? Okay, Jenna. Help me out here. What's this? Like, how do you do that? Talk me through that. So when I say plug 2 plus h into the function, what does that turn into? Yeah, 2 plus h is going to go in right here, right? So we're going to do 2 plus h in parentheses, and we're going to square it. That's the top left-hand corner of that. Yes? That's 2 plus h into the function. Keep going. Minus? Minus 4, right? Because you're going to plug 2 into the function. Oh, sorry, into the function. So 2 squared is 4. Over h. All right? If you were doing the problems here with me today, if you flip back in your notes, look at the problem we did x squared at x is 2. When we did this limit setup, notice how different those limits look, right? The one we had was x squared minus 4 over x minus 2, wasn't it? This one is 2 plus h quantity squared minus 4 over h. Totally different looking limits, right? So let's see what sort of algebra I can do here. By the way, you do get 0 over 0. If you let h go to 0 right now, you get 0 over 0. Y'all believe that? If that goes to 0, that's 2. 2 squared is 4. 4 minus 4 is 0. So you get 0 divided by 0.